All right, so today what we're going to do is we're going to review empirical and molecular formulas, and we are going to learn how to calculate empirical and molecular formulas from data. So just a quick review. Recall that in a formula we only have a whole number of atoms, whether this is empirical or molecular. You can't have a fraction of an element. In an empirical formula, it's going to be the simplest ratio that these can combine in. So for instance, if we were to look at hydrogen peroxide, H2O2, this would be the molecular formula, whereas if we simplify this, the ratio is 1 hydrogen for 1 oxygen. That would be the empirical formula. So we can calculate the empirical formula if we're given the relative mass of the components. So we can either be given the masses or we can be given the percent composition. But once you know that, we need to determine the moles, because remember, whenever we're looking at a chemical formula, we're looking at the ratio of atoms. So H2O2 tells us there's 2 hydrogen atoms to 2 oxygen atoms. Or the empirical formula, there would be a 1-to-1 ratio between hydrogen and oxygen, which means that if we had a mole of this compound, there would be 1 mole of hydrogen to 1 mole of oxygen. And the way that we can get this ratio is we can divide by the smallest number of moles. So that's the strategy that we're going to use, and we'll try an example here in just a second. But one of the ways that students in the past have learned this concept is they've sang a song. So what they did is they did percent to mass, mass to moles, divide by small, multiply to whole. All right, so let's go ahead and try to practice this. So in this particular example, we have a 2.5 grams of a compound, and we have determined that 0.9 grams of this compound is calcium, and 1.6 grams of this compound is chlorine. So what we need to do is we need to calculate the moles of each so we can figure out the ratio that these combine in. Let's go ahead and try that. So we'll start with our calcium. So we'll have 0.90 grams of calcium. And then to convert this to moles, we'll say 1 mole of calcium is 40.08 grams. Okay, so that's the molecular weight, or the atomic weight that you could get off the periodic table. Whenever you plug that in, that will give you 0.022 moles of calcium. Okay, so now let's go ahead and do the same thing for chlorine. So we have 1.60 grams of chlorine. So to convert that to moles, we'll have to divide by the molecular weight. So in 1 mole of chlorine, there are 35.45 grams of chlorine. Whenever we plug that in, we get 0.045 moles. Okay, and here, the sig figs aren't going to be important as they are in other problems, because we have to end up getting an integer value. So if you don't get an integer value after this next step, then you might need to go back through and add some sig figs. But we're trying to figure out the ratio of calcium to chlorine. So if you go back and think about our rhyme, percent to mass, well, our values were already given to us in terms of the mass. Mass to moles, so we've converted both of our masses to moles. So now it's time to divide by small. So which one of these is the smallest? Well, 0.022 is in fact smaller than 0.045 moles. So what we'll do is we'll go through and divide by 0.022. And whenever you go through and divide by that, this tells us that for every 1 mole of calcium, there are 2.05 moles of chlorine. Okay, well, this is close enough to 2. Okay, so we can just ignore this part right here. So just remember that we can't have a fraction of an atom present. So what is the empirical formula here? Well, the empirical formula would be CaCl2. So one of the next logical questions should be, how do we know when we can't round, and how do we know when we need to multiply till whole? Okay, so after dividing by small, you want to look at your values. So after we divided by small up here, we got 1 mole of calcium, and then we had the 2.05 moles of chlorine. You want to look for big fractions, because especially for this class, things are going to be combining in fairly common ratios. So you'll know you need to multiply till whole if you get something with a decimal or a fraction that is a multiple of 1/3. So look for a multiple So you could look for 1/3. So this would be if you had something that was 0.33 or 0.66, something like that. That would be fairly common. You could look at 1/2. So if you saw something that was 0.5, maybe even 1/4. This is less likely. The third or the half, that fraction is going to be more common, but then you'd look for something that was 0.25 or 0.75. And in rare cases, you might have to worry about a fraction of 1/5. And that would be where you would have 0.2, 0.4, 0.6, or 0.8. But that would be extremely rare. Okay, but remember that the simpler the ratio is, the more plausible that that formula will actually work for that particular compound. Okay, so that's how you would find an empirical formula. Let's go ahead and try to find a molecular formula. So a mystery carbohydrate is composed of 25% carbon, 8.3% hydrogen, and 66.7% oxygen. What is the molecular formula of this mystery compound, assuming the molar mass is 144.15 grams per mole? All right, so the first thing that we should probably do before we find the molecular formula is we need to start by finding the empirical formula. Find empirical formula first. Okay, so if we're going to find the empirical formula, remember our saying, percent to mass, mass to moles, divide by small, multiply till whole. Okay, so the easiest thing to do is to go ahead and you want to make an assumption since you're given percents instead of masses. Let's assume you have 100 grams. If you assume you have 100 grams, then you can convert those percents directly to masses. So we would have 25.0 grams of carbon. We would have 8.3 grams of hydrogen. And we would have 66.7 grams of oxygen. Okay, so that's the percent to mass. So now for the mass to moles, we have to go through and divide by the molar masses or the atomic weights here. So we have for every 1 mole of carbon, 12.01 grams of carbon. So this will give you 2.08 moles of carbon. And then for hydrogen, for every 1 mole of hydrogen, 1.01 grams of hydrogen. This will give you 8.22 moles of hydrogen. And then for oxygen, you will need to go through and divide by its atomic weight, which is 16. That will give you 4.17 moles of oxygen. Okay, so again, that takes care of percent to mass and mass to moles. So now we need to divide by small. So the smallest number of moles here is 2.08. All right, so whenever we go through and divide by 2.08, we end up with 1 mole of carbon, 3.95 moles of hydrogen, and 2 moles of oxygen. So I would say that this 3.95 is close enough to 4 that we can round it. So that means our empirical formula is CH4O2. Okay, so if we're trying to find the molecular formula, we need to figure out how many times does this empirical unit right here, how many times does this go into the molecule? So what we need to do is we need to go ahead and find the empirical weight. So you should have practice finding molar masses, formula masses. So go ahead and find the empirical weight for this compound right here, or this formula right here, CH4O2. What you should find is it's 48.05 grams per mole. You might want to double check that. So if we want to figure out how many times does this go into the molecule, what we can do is we can take the molecular weight divided by the empirical weight, and that's going to give us some factor. And that's going to tell us how many times does that empirical formula actually go in the molecular formula. So let's go ahead and take the molecular weight, which is 144.15 grams per mole, divided by our empirical weight, which is 48.05 grams per mole. And that gives us a factor of 3. Okay? So what that means is we are going to take our empirical formula, the CH4O2, and we're going to multiply it by 3. So you could write it like this, or you could go ahead and distribute and say C3H12O6. Okay, so that's how you would find the molecular formula if you were given a percent composition and the molecular weight. You would have to find the empirical formula first, and then you would find the empirical weight and determine a factor. How many times does that empirical weight go into the molecular weight? All right, so that will conclude today's lecture. And then next time we'll start to talk about molar concentrations. We're going to start to look in the aqueous phase, figure out how to deal with moles in an aqueous solution.